In this video, we will be working examples on isothermal process, isochloric process, and isobaric process, if we have enough time. Okay, the first question: 1 mole of an ideal gas at 300 Kelvin is allowed to expand isothermally against a constant external pressure of 1 bar. From a volume of 1 liter to a volume of 5 liters, find the work done by the gas and the heat absorbed from the surrounding. So we are looking for W and heat. Then find the work necessary to compress the gas back to its original volume, and then find the work done by the gas if the process takes place reversibly. Okay, the first part of the question, it's always nice to write out all the parameters that one has. So the question is 1 mole, which means N equals 1, of an ideal gas at 300 Kelvin, T equals 300 Kelvin, is allowed to expand isothermally, which means delta T equals to 0 against a constant external pressure of 1 bar. Conversion ratio factor 1 bar is 10 to 5 Pascal. From a volume of 1 liter, 1 liter is 10 to minus 3 meter cubed. So a volume of 5 liters, that's 5 times 10 to minus 3 meter cubed. Find the work done by the gas. So we're looking for work, that's why it's question mark. And the heat absorbed from the surrounding, that's another question mark. Okay, so the first thing to do, work is a minus P external P. Work done is P external dV integral from V1 to V2. And since P is constant, it can come out of the integral, and the integral simply becomes V2 minus V1. So we can put in the values that we have. P external minus 10 raised to power 5 Pascal, that's Newton per meter squared, times 5 into 5, that's V2, minus 1. So if we plug this into a calculator, we arrive at minus 400 joules. Now, since from the first law of thermodynamics, the next question is find Q. From the first law of thermodynamics, the change in internal energy is equal to Q plus W, which implies that Q equals minus W. Because for an ideal gas, U is a function of T only, and our U is equal to 0. Therefore, our Q equals minus W. So minus 400 is positive 400 joules. The second part of the question is find the work necessary to compress the gas back to its original value. Okay, to obtain this, we need to calculate the initial pressure of the gas. So initial pressure will be calculated from the initial conditions, which is V1. The temperature is constant, so we need to calculate the initial pressure in which the gas was before it was allowed to expand to V2. So if we put this into the ideal gas equation, PV equals to nRT, where we make P the subject of formula, it becomes nRT over V. N is 1 times our gas constant, 8.314. The unit is in joules per Kelvin per temperature, per mole per Kelvin, and our temperature is in Kelvin, and volume is in meter cube, which is also SI unit. So we have everything in SI units. Punching this in the calculation gives us 24.9 times 10 to the power 4 Pascals. So why did we calculate this? Because we need to compress the gas back to this pressure. Therefore, the work done for the compression must have our 24.9 times 10 to the power 5 Pascal as the external pressure for the compression. So this gives us W is minus P external into V2 minus V1. So our P external in this case is now 25.9 times 10 to 5 into, so the final volume in this case is 1 minus 5. If you plug all this, so this is a conversion unit to meter cube. So we have at 9,976 joules. That's about 9.98 kilojoules. Since this is not equal to what we have in the previous calculation, so let's quickly just go back to it. In expanding from 1 to 5, the work required, the work done, so the system did a work of 400 joules, but in taking it back to the system, 9,976 joules is needed. Because these two values are not equal, the process is not reversible. So we go back to the third part of the question. Find the work done by the gas if the process takes place reversibly. If the process takes place reversibly, the work done for a reversible process is minus nRC ln V2 over V1. Again, we remember our parameters. The pressure is not needed in this case because it varies with the volume as the volume changes. So, putting it all our values, N1 times 8.314 times temperature, natural log of V2 over V1, that's 5 over 1. We put this into the calculator, we arrive at minus 4,014 joules. So the question is, if the process, find the work done if the gas, takes place. So that's the work done if the gas takes place reversibly. Okay, so out of curiosity, you note the equation describing this involves only the initial final volume. So if we were to compress it back, it means that our final volume is now 1 and 5. The work done will be 4,014 joules. So these two values are the same, and that shows that it's a reversible process. Okay, another example. An ideal sample of methane, which means methane behaving like an ideal gas, occupies of mass 4.50 occupies 12.7 liters at 310 Kelvin. Calculate the work done when the gas expands isothermally against a constant pressure of 0.3 atmosphere. So, in this, we're given the change in volume, which is 3.3, P external is 0.3 atmosphere and can be converted to pascals. W is pressure, that's supposed to be capital P, not small letter p, minus v. So we have it as 0.3 times, in pascals, 101325 times 3.3, and converting this to meter cube, that's equal to minus 100 joules. The maximum work possible is always the reversible work done. So that's the maximum work that the system can do at that temperature. So this is N minus nRT ln V2 over V1. So that's the second part of the equation. N is 4.5, that's the mass, divided by the molar mass of methane. Methane is CH4, carbon is 12, and we have 4 atoms of hydrogen. That's hydrogen is 1, so that's 4 plus 12, 16. And we arrive at 0.28 moles. If we slot it in the equation, we have minus 0.28 times 8.314 times 310. Natural log of 16 over 12.7. Now this 16 is not the molar mass of methane. It is the final volume obtained by 3.3 plus the initial volume of 12.7. So that gives us minus 166 joules. So that's the maximum work that the system can do. Another example, calculate the work done on the surrounding if 1 mole of neon, assumed to be ideal, is heated from 0.0 degrees centigrade Celsius to 250 degrees Celsius at constant pressure of 1 atmosphere. So N is 1, T1 is 0.0, that's 273 Kelvin, T2 is 523 Kelvin, that's 250 plus 273, and pressure is 1 atmosphere, and we to calculate work done. It's a constant pressure process, so P can come out of the, so work is minus integral P dV, and P can come out of the integral, and we have it as minus P delta V. Since P is constant, since P is, okay, so, but initial volume was not given, we can calculate it from the ideal gas equation, PV equals nRT. So V will be the initial temp, using the initial temperature, we calculate, we obtain 22.4 liters. N is 1, R is 0.081. Note that we're using 0.0821 for R because we have kept our pressure in atmosphere. It was not converted. Similarly, we can calculate V2. We can also calculate V2 by nRT2 over P, or we can use Charles' law to calculate it, and we arrive at 42.9 liters. So we can calculate our W now. 101,325. That's converting it to pascals into 42.9 minus 22, and 1,000 divided by 1,000 to convert the volume from liters to meter cube. So this gives 2.1 kilojoules. So far, so we have talked about isothermal process. Delta T is 0, and because of that, delta U is 0, which makes Q to be minus W. The irreversible work done for isothermal process is minus PV2 into minus V1, and for the reversible isothermal process is minus nRT ln V2 over V1. For an isochoric process, that's a constant volume process, delta V is 0, therefore W is 0, and delta U is Q, and it's supposed to be a QV. For an isobaric process, delta P is 0, W is minus P delta V, and delta H is QP at constant pressure. See you in the next video.